Okay, I have two word problems here. Ultimately, I just took the guts of it, but I will first read the word problem. They don't give a drawing, and sometimes that's the hard part of this. Certain problems that give you a drawing make it much easier, right? Sometimes it's hard to visualize exactly what they're talking about. I don't think these are horrible, but two great examples. They come up quite often in a trig class. All right. So the first example, a radio tower is located 400 feet from a building. Okay, wrote that. From a window in the building, a person determines that the angle of elevation to the top of the tower is 36 degrees and that the angle of depression to the bottom of the tower is 23 degrees. How tall is the tower? Now, with a simple tool, and actually we could even build one to get approximately this, we could use trig and solve these things pretty simply. The one thing I guess we would need to go outside and really measure is, like, if we were doing this, is this tower truly 400 feet from the building? So, okay, if you knew that, yeah, this problem is very possible with very simple tools. All right, so we have some tower, okay, radio tower, whatever, we'll pretend it has an antenna with my beautiful drawing here. Okay, that's a tower. And we're in this building over here. Okay, we're somewhere right here. We'll just pretend, because the angle of elevation and depression, we have both. So what does that mean? Angle of elevation means if you were to draw a horizontal line, then that's the angle that goes up from the horizon. Okay, we call this line the horizon, and that angle that goes up is the angle of elevation, 36 degrees. And we know that this horizon was 400 feet because it was given. We're 400 feet from this tower. Okay, the angle of depression, now I'll always claim in anything I do it's not to scale, because I didn't try to get this exactly 36 degrees or 23 degrees. This is simply a picture to kind of help us see what's going on. Okay, so the angle of depression to the bottom is 23. And maybe mine isn't horrible. And what we're trying to get is the overall height of this tower, right? How tall is that? So, I don't have a 90 on the left over here because, right, 36 and 23 is 59 degrees. So, don't have a right triangle there, but we do have two right triangles because since we drew this with the horizon, right, the directly across, it's perpendicular. Now I can set up two trig functions and break it down piece by piece by finding this top part, right? Call that x1, and then this bottom part, x2. I should have not been lazy here. There we go. Call that x1 from here to here, and then this x2 from here to here. There we go. That's more legible. All right, let's set up some trigs. So we have, in both of these, we have opposite and adjacent, which again is tangent. Tangent 36 degrees equals opposite x1 over adjacent 400. Tangent 23 degrees equals opposite x2 over adjacent 400. Okay, these are pretty simple to solve because we just need to clear the denominator by multiplying by 400. So we'll take our calculators and do 400 times tan 36, 400 times tangent 23, and we will have to sum both of those answers, right, for the total length. So 400 times tangent 36, 400 36. Again, make sure you're in degrees. Get about 290.61. This is given in 400 feet. Often a good rule of thumb of how much do you approximate is whatever your result is in. Often, though, you don't really want to approximate too much while you go, though, so we'll just say it's about 290.6 for now, but our final answer will round to a whole number. Right? 400 times the tangent of 23 degrees is 169.8, about. So now sum those. 169.8 plus 290.6. And again, because you're using a calculator, we could have got this, as precise as we choose to. Overall, we get 460.4. I'm just going to say 460. The length, that tower is approximately 460 feet tall. That says tall. Right, since we summed those two together. Awesome. All right. In this next example, 33-foot ladder, so let me go ahead and read the entire problem, but I think what I have is almost everything. A 33-foot ladder leans against a building so that the angle between the ground and the ladder is 80 degrees. Okay, I wrote all that. How high does the ladder reach up the side of the building? Okay, so we have some building here, and this ladder, 33 foot, 80 degrees is a steep angle, so I'll draw approximate. Here's my ladder, pretty steep, 80 degree angle here. It doesn't necessarily say it reaches to the top, right? Reach up the side of the building. So here, we could quickly fix that. There we go. There's the building. It's going up the side, and we want to know how far up. So that is our X. What else do we know? We know this ladder is 33 feet. All right, solving for X then, from this angle, we have opposite and hypotenuse. So SOHCAHTOA, opposite and hypotenuse, involves sine. So let's go ahead and do that. Sine of 80 degrees equals opposite over hypotenuse. Simple algebraic equation. Well, trig is sine, but solving for X, we just do multiply 33 times the sine of 80. 80 is not on the unit circle. We need a calculator. 33 times sine of 80 is, we get 32.49. 32.5, we'll say. I guess we could round down to 32. I want to leave it at that for this one, and here's why. If this was a 33-foot ladder and I claim that it goes up 33 feet, then that would mean the ladder is simply straight up, right? It's vertically on the building. It's resting it against the side of the building. So I know it can't be 33. It's got to be under that. 80 degrees is a very, very steep angle, though. So the fact that it went almost 33 feet does make sense. If this were a 10-degree angle, right, then that ladder's like down here against the building, then it really wouldn't make sense that this 33-foot ladder went up 33 feet against the building. Okay, the steeper this angle, the closer this opposite side is to what the hypotenuse would be. So how high up does the ladder reach? It reaches approximately 32.5 feet up the building.